Okay, this will be a very quick introduction to CROTOR, which is a propeller design and analysis program. So I've provided a couple of links here. You really only need to worry about the CROTOR link. CROTOR is based on a Drela program, same professor who wrote Xfoil. He also wrote QProp. These are both pretty useful tools if you want to get down in the nitty-gritty of doing some propeller analysis. Since CROTOR is based upon XRotor, I recommend just using that straight off, because it does have a couple of features over and above that built into XRotor. But it does primarily run the XRotor framework. It just has a couple different options built on top of that. So the first thing I recommend you do, go to the CRotor webpage, read through this before you download anything. It does have Windows and Mac binaries that allow you to run that pretty much straight out of the box, just like you've done with Xfoil. It does come with several different programs, primarily for doing some parametric analysis and lofting. Say you want to make your own propeller, actually construct it. Has that capability to provide output into SolidWorks, for example. We're only going to be using CRotor, so that's the only thing that we will go over. There are some example plots here that we'll come back and take a look at. So let's just jump right in and go ahead and run XRotor. What you'll notice first off the bat, it's going to have the same type of file structure and directory structure that you have in Xfoil. So every command is typically going to be a 4-letter command, sometimes followed by an input parameter. Anything preceded by a period indicates that is a lower directory tree, so that will take you to a subdirectory. So one of the things that you'll do for this particular homework problem is you will load up a propeller. So I believe we called it either simple or sample, or a couple different options here. We'll go ahead and load up the sample prop, and as soon as you do this, it provides you with some characteristics for that particular propeller. Notice all the units are going to be in SI units, so propeller geometries are going to be in meters, thrusts are going to be in newtons, power is going to be in watts. It will calculate torques for you on the propellers, so that way if you have a shaft output torque, you'll know what that torque is, and that's going to be in newton meters. Speed of the aircraft, so this is your flight speed, is going to be in meters per second. You'll also have RPM, as well as viscosity that you're working with. Your Reynolds number and density will be calculated off of those. Speed of sound, so that way you know what the tip Mach number is going to be, which is an important propeller defining characteristic. And then it will give you your propeller geometry as a function of stations starting at the hub all the way out to the tip. So your local radius, your non-dimensionalized chord length, your beta, which is going to be your twist angle of the propeller, and then your aerodynamic characteristics, things such as CL and CD. So we're not going to use this particular propeller. We'll upload some others so that we can take a look at those. Before we do that, there are a couple other kind of menu commands that I want to go over. First of these are airfoil characteristics. So every propeller is going to have a basic set of airfoil characteristics that you're going to define the propeller around. And most propellers are going to be blended. They're not going to have a single airfoil characteristics across the entire prop. For this simple example, we are going to have a single propeller that we're using across the entire range from the hub all the way out to the tip, and those are defined from some very simple aerodynamic parameters, just like we would define any particular airfoil. Things such as the zero lift angle of attack, the DCLD alpha in radians, the value of DCLD alpha at the stall angle of attack, maximum CL, minimum CL, CL increment to stall once it gets to the stall angle, and then some other basic drag parameters as well. So this will allow you enough information to essentially construct what that lift, curve, slope, and drag polar looks like for that particular airfoil section. As I mentioned, we're just going to use some simple propellers that are using the same airfoil cross section across the entire radius of the propeller, even though the chord length is going to change. You can add some additional aerodynamic sections in here and define different propeller airfoils that will perform differently. And the reason that this is typically pretty important is since the propeller is a rotating airfoil, you end up with a variety of different Reynolds numbers across that range of props. And so you'll typically optimize propeller for different Reynolds numbers. Now this submenu will allow you to look at some various airfoil drag polars. So for example, you can look at the variation of Reynolds numbers across a range of drag polars. So you can see those here for the kind of variety of different Reynolds numbers, starting off 100,000, working up to 400,000 in this particular case. See the impact of Reynolds number for that particular set of airfoils, and do the same thing with Mach number in this case. So you can see the impact of that drag divergence at the higher Mach number ranges, particularly when you start to get into the transonic Mach numbers around 0.8 and 0.9. This is going to be particularly important for propeller, so it is not uncommon for our propeller tip speeds to get into transonic velocities, and that's one of the things that we want to be able to design around. So let's go back up one menu, and in this case, pulling up our commands again, there are some things that you can come in and take a look at in terms of the rotor geometry. Designing a rotor geometry is actually pretty straightforward in this case, inputting several different parameters, and when you get to the point, if you have a propeller driven aircraft design, this is something that the propulsion team should be working on and playing around with some different propeller options to look at. And once you have propeller geometry, you can also modify that propeller geometry. So you have some basic options within the design menu. Primarily, you're just going to input basic design parameters, and you can change the variety of parameters that you have. And then once you have the basic design, then you can make modifications to that design and basically look at the different geometry that you have. So let's go back and actually pull up load our other propeller that we're going to be working with, and then we'll go to the operations menu in this case. For those interested in doing lofting, you can do that here again within this kind of geometry design menu. Once we have the propeller loaded, working with our basic aerodynamic parameters, then we're just going to work in the operations menu. Again, there are a lot of other powerful things that you can do with parametric analysis within this particular program that we really aren't going to explore in much detail. So we're just going to really scratch the surface of the basic capabilities. So within the operations menu, just like you have in the operations menu of Xfoil, you have a lot of options that allow you to go through an analysis of a basic propeller. So the first is you can plot some basic rotor parameters to take a look at your propeller. And so in this case, plot 1 shows you your basic blade geometry. So this just shows you a single blade with what it looks like from both the axial and the lateral perspectives, and then what it looks like if you take that beta twist out of it. And then this also just shows you how much twist you actually have into the basic propeller or propeller blade. Plot 2 then actually shows you that propeller geometry, and so you'll see in this case this is a two-bladed propeller, and it gives you some basic propeller characteristics, the radius, the area, your hub diameter, the amount of beta twist that you have, and then your blade solidity at the 3/4 location. And then plot 3 will actually show you your aerodynamic or your performance parameters for this particular propeller. So this is just a simple general aviation propeller. 2 blades, a radius of 0.9 meters, so a diameter of 1.8 meters. Important operating parameters in this case: velocity of 50 meters per second, advance ratio of around 0.8. You can see your power and thrust coefficients, your output thrust at the required power that you have, and then the operating RPM. So this shows you that basic cross-sectional performance for your airfoil across the blade, starting at the hub location, so you're not getting any benefit of the prop out in this area. That's because you actually have to mount the prop to your engine shaft on your engine or your motor. So you can see the efficiency, local efficiency across the entire prop, and then you can compare this with your total efficiency, and then what would be compared with your ideal efficiency, not taking into account losses. Then you actually have your lift parameter. So this is essentially your local circulation value that you have across the blade. So this is how you're calculating the lift. So notice that you're tending to get a lot of lift kind of at the outer section of that prop, and that is because you're rotating at a faster velocity. Again, this is spinning as a solid body, so closer to the hub, even though you're spinning at the same RPM, that local velocity is actually pretty low, right? And that is also observed within the value of the local Mach number that you have, starting off a relatively low value and then working your way up out towards the tip. And this is, these are plotted on the left axis here with your local lift coefficient. And notice we have a constant lift coefficient since we're working with a constant airfoil, and all we're doing is just changing that local value of the twist to keep that lift coefficient constant, starting at the hub going all the way out towards the tip. And that's really it. That's kind of the basic operating parameters that you have. So then you can come in and you can play with different ranges. So if you want to, say, calculate a sequence of advance ratios or look at a sequence of RPMs. So for example here, if we wanted to see what the variation would be around a range of RPMs, let's just do some simple cases starting at a range of 1500 going to 2500 in increments of 250 RPM. And we'll do this for a fixed power case, essentially keeping our power constant. We could also do this for a fixed thrust case or a fixed blade pitch angle. And then this will run through this for us and then plot our value of our parameters. And then we can repeat this for a range of different parameters. So let's do this again for a sequence, same range. But now in this case, we'll do a fixed thrust solution. Okay, and you can see your limits here, and then the ranges you're getting across that value of RPM, your local efficiency that you have, and then your thrust and your power coefficients. Okay? And it tells you what ranges your propeller is actually going to be able to operate in for that particular case. You can do the same thing with a sequence of advance ratios, or you could do something pretty simple as, hey, I'm going to take this basic propeller geometry set of parameters that I have right here, and then prescribe something such as the RPM. So rather than working with 2000, we could say, well, I'm going to back down my RPM to 1750, and then see how my basic airfoil or my propeller performs. So again, this is pretty straightforward to allow you to look at a range of different input parameters to see how well that propeller is actually going to operate. Okay, so now what you want to do in this particular case then is come back and make modifications to the geometry, because what we want to do with this particular problem is we want to take this basic set of operating parameters that we have for the baseline case, and in this case we will have an RPM of around 2000, And these are going to be our baseline parameters. So given these parameters, basically primarily our thrust and our power output at this particular velocity that we have, is it then possible for us to come back and reduce our tip Mach number to a value below 0.3? And that's primarily for noise considerations. If you're able to get that tip Mach number down to below 0.3, you can essentially make your propeller really, really quiet in that case. And you're primarily just hearing engine noise in this case rather than actual propeller noise. So you'll have to go back and go up to the geometry modification and start playing around with these different parameters that you have, such as blade number, chord distribution, tip radius, so you can change the actual size of the propeller, shrink it down a bit. So given the same value of RPM, if you're rotating at a lower, or the same value of RPM if you have a lower or smaller radius, then obviously you're going to have a smaller tip Mach number as well. And so as an example, this is a 3-bladed propeller solution. So you can see our basic geometry here in our 3-bladed prop and what that particular case looks like. Okay, so again, just kind of gives you an example to start from and to start playing around with. Now, propellers are pretty complex things, and it's pretty difficult, you know, to essentially make one propeller fit a wide variety, and that's why we obviously have things such as constant speed props or variable pitch prop that allow us to go through the process of changing those angles. And that, in this particular case, where we can, you know, vary things such as the basic operating parameters. So, you know, things such as changing the blade angles. You're looking at speeds at fixed pitch, so you could have a fixed pitch prop, for example, and see how well it actually works. That's enough to kind of get your feet wet for this particular homework problem, so that way you can play around with things and go from there. We'll come back to this and take a look at some more advanced CROTOR operations within the future.